Hello, my awesome AP Chemers. Today we're going to talk about ionization energy and the trend for it on the periodic table. So let's first define what ionization energy is. It is the energy required to remove the outermost electron from a gaseous atom. To remove the outermost, so a valence electron, from a gaseous atom. The units that we typically use, it's an energy, so joules or kilojoules, but usually we report it in moles. So it's usually kilojoules per mole. And ionization energy is basically a measure of the effective nuclear charge, or the net Coulombic attraction between the valence electrons and the nucleus. And so the farther the valence electron, the weaker the net Coulombic attraction between it and the nucleus, and therefore easier to remove and requires less energy to remove that electron. So if I'm trying to remove electrons, all the way out here versus something that's closer to the nucleus here, these are much easier to remove. These would be much harder to remove. Again, because these are experiencing a much stronger attraction to the nucleus versus these. So if we were to look at the trends on the periodic table, as you go across, the ionization energy increases, and as you go down, it decreases. Now remember, both ways, whether you go across or down, you're adding more electrons and you're adding more protons. So the key is, where are you adding those extra electrons? So in this case, your extra electrons are in the same energy level, so the extra shielding is really minimal. So since it's about the same shielding, what we care about more here is that there are more protons. And remember, you can just ignore this part in your explanation if you'd like. You can just say there's more nuclear charge, more protons in the nucleus, so the net Coulombic attraction is stronger. And therefore, these valence electrons are held tighter and harder to remove and require more energy to remove them. As you go down, your valence electrons are occupying higher energy levels. And please be careful, don't say there are more energy levels, say there are more occupied energy levels. Those valence electrons occupy a higher energy level. Because remember, all atoms have an infinite number of energy levels, so just be careful of your wording. So because those extra electrons are at a higher energy level, which means they're farther away from the nucleus, the net attraction between the nucleus and the valence electrons is lower, therefore it's easier to remove them and require less energy to remove them. So let's take a look at this graph here, and it's missing a bunch of labels, so I'm going to go ahead and label these. So let's look at the second period first. So this is lithium, so this must be beryllium. This is boron, carbon, nitrogen's labeled, this is oxygen, and then this is fluorine. I'll label the next period as well. So sodium, magnesium, aluminum, silicon, phosphorus is labeled, and then we have sulfur, chlorine, and argon. All right, so let's take a look at just one of these periods. So let's look right here. As you go across a period, it does look like, the trend is true, that it is increasing as you go across a period, but there are a couple of exceptions. Look at boron and look at oxygen. Those are not where they're supposed to be, right? Boron should be like right here. Oxygen should be right there. Same thing if you look at this period. In general, it's going up, but aluminum is not where it's supposed to be. Aluminum should have been here. Sulfur should be a little bit higher. And so it seems like group 13 and group 16 are kind of exceptions. They're not following the trend. as you go down a group, it decreases. It looks like that trend is true. So we look at lithium, sodium, potassium, rubidium, cesium, francium. It does look like it is decreasing, so that's good. So the down a group trend seems to be fine, but the across seems to be a little, you know, two spots where it doesn't hold true. So let's look at these groups and see why are they not following that trend. And by the way, on the test, you would follow that trend if they ask you for 2 elements, but they might ask you to explain why are these groups different. Like they could tell you, hey, boron and beryllium, you know, we should expect boron to be higher than beryllium. Why is it lower? So you can explain that. So I think the best way to explain it is if we look at the electron configurations for these. So let's take aluminum as an example, and let's show the electron configuration for aluminum. So aluminum, you can write it as, this is neutral aluminum, you can write it as neon for the shortcut. And then you have 3s, and you put 2 electrons in the 3s, and then you have your 3p. Okay, now ionization energy means you remove the outermost electron. Well, the outermost electron would be this one. So let's look at it if we were to remove that electron. So it'd become neon, 3s with the 2 electrons, and then 3p, and this would be empty, right? Remember that from last year, we talked about that if you have a sub-level that is completely filled or half filled, then that's a pretty stable configuration. When you have a sub-level that's just like has a random number like that, then it's not very stable. So, excuse me, that electron here, in order to remove it, it requires energy. It's still attracted to the nucleus, right? But it doesn't require as much energy as we think it would. The reason is because when you remove an electron from aluminum and it becomes Al+, the result is a spin-paired configuration. We call this a spin-paired configuration or a complete sublevel. You can say the 3s sublevel is complete. There's nothing in the 3p, which is relatively a stable configuration. Again, we're not saying that this is more stable than or that this is more stable than this. What we're saying is that yes, it will require energy to remove the electron, but not as much as expected because your result is a spin-paired stable configuration. Okay, so it requires energy to remove the 3p electron, but not as much as expected because the result, Al+, has a stable spin-paired configuration. Now watch out the way you word it. Don't say that this is more stable configuration than this one. It is not. It still requires more energy. It still requires energy to remove it, but it's not as much as you would expect. Okay, let's look at group 16. So let's look at sulfur, and the Aufbau diagram for sulfur would be neon still, and then you have your 3s with 2 electrons, your 3p with 4 electrons. Now, if I were to remove the outermost electron, I'd get 3s with the 2 electrons, but then now the 3p has just 3 electrons, so 1 in each. Now, it's not that this configuration is better than this. It's just that relatively this is a stable configuration. Not more stable than this, but relatively stable configuration. So it still requires energy to remove that electron, but not as much as we would expect because the result is a half-filled 3p sublevel. One before it had 4. So you'd say the same exact thing. You just say half-filled 3p sublevel. So you'd say the same thing as this, except the result, which is the S plus, and then you'd say this instead of this right here. So that's if you're just talking about just one of the elements. If you are comparing two different elements, like let's say we compare aluminum with magnesium, and we say, I'm going to do it on the side here. So for magnesium, I have neon and 3s. And then Mg plus would be. So you'll be asked, like why, let's see, aluminum is lower than magnesium. So if that was the question, you need to address both. So I would write this whole thing and write all this, say that it's lower than expected, whereas this one, you are removing that electron, so you're going from a spin-paired configuration to a half-filled configuration, which is not as favorable as going from 1 in the p to a spin-paired configuration. So just address both elements if you are asked about both elements, but it's really the group 13 and the group 16 that is not normal. The rest of the elements, like magnesium, follow the normal trend. Okay, a new topic for this year that we didn't really talk about last year is that all this that we've been talking about is the first ionization energy. That trend, when it increases across and decreases down, that's for the first ionization energy. That means to remove just the one outermost electron. Well, once you remove that one electron, well, maybe you can remove a second electron or a third electron or a fourth electron. So there are subsequent ionization energies. So second and subsequent ionization energies increase as Coulombic attraction of remaining electrons to the nucleus increase. What does that mean? That means that once I remove the outermost electron, well, now you have less electrons to repel each other. So if I try to remove that second electron, that would require even more energy. And if I remove 2 electrons, now you have 2 less electrons, so less repulsion. So more between the electrons, so more not Coulombic attraction between the nucleus and the remaining valence electrons. So it's even harder to remove a third electron and even harder to remove a fourth electron and so on. So the ionization energies actually get higher and higher and higher with the second electron being pulled away, or the third or the fourth, and so on. So let's look at fluorine, for example. So in order to remove the first electron, you need 1,680 kilojoules per mole of energy. In order to remove a second electron, look at that, it almost doubles, right? You need double the amount of energy. In order to remove a third electron, that's double the second one. Next one is even more. Next one is even more. Next one is even more. So that is true for any element. The more electrons you remove, the more energy is required, because the remaining electrons that you have, once you've removed one, the remaining electrons that you have are experiencing more net Coulombic attraction, stronger net Coulombic attraction to the nucleus, since there's less repulsion from the electrons, since you've removed some. In general, not always, but in general, it seems like it about doubles or so as you go from one to the next. As we saw here, this one, that jump is about double. This jump is about double. This one's not quite double, but it's, close, right? Between 1 to 2 times, right? If you see a huge jump, so if it's like 10 times, then that means that you have removed a complete energy level, and now you're the next one that you're removing is a core electron. It's from the previous energy level. So what do I mean by that? Let's say you have lithium. So take a look at lithium. Lithium's electron configuration is, I'm going to write it up here, 1s2, 2s1, right? So if I remove that first one, if I remove this, requires quite a bit of energy, right? 520 kilojoules per mole. But once I remove this one, if I'm trying to remove some from the 1s, that's even way closer to the nucleus, right? So it's way stronger attraction. And so it goes up by like 14 times, right? Going from 520 to 7,297, that's like 14, 15 times, something like that. Now look, so if I were to remove one of these, then I'd be left with just one electron in the 1s. The third one, yes, it's a little bit more, right? But not, you know, again, double or a little bit less. So that tells me that that second electron is from a different energy level compared to that first one. So that tells me that lithium has one valence electron, because once I remove it, I go to the next level. Let's look at a different one. Let's look at nitrogen. Nitrogen has 5 valence electrons, right? So the electron configuration for nitrogen is 1s2, 2s2, 2p5, right? Oh, sorry, 2p3, not 2p5. So the first 3 looks like I'm doubling again. So this is the first one that I remove. This is the second one I remove. This is the third one I remove. These are my 2p3, right? Once I remove those, I'm going to the 2s. The 2s is in the same energy level. So again, it's increasing by, you know, double or a little bit less than double, right? So this is a 2s electron. This is another 2s electron. Now, once I remove all of these and I expose now these electrons, these are in a different energy level. These are called core electrons. And so they are way, have stronger attraction to the nucleus. And so look at this jump. I go from 9,000 to 53,000. So that's nowhere near double, right? That's more than 5 times. It's almost 6 times. So that tells you that this element had 1, 2, 3, 4, 5 valence electrons. So where you see a big, huge jump like that, that tells me that those were the valence electrons, and now I'm removing the core electrons. Okay? All right, so this here is explaining what we just talked about. So this is your ionization energies increase because this is because as electrons are removed, there is less mutual repulsion between the electrons, so the radius is smaller. This makes it more difficult to remove the electrons, so subsequent ionization energies increase. This is showing you what it looks like as an equation. So we're missing the arrows here. Just put them in. And so if this was a neutral atom and I'm removing an electron from it, I have to put in this much energy. That's the first ionization energy, right? And I get this cation with a positive charge and then the electron. If I were to take this and try to remove a second electron, then I have to put a second amount of ionization energy, which is greater than that one, and I get a 2+ ion. If I take that 2+ ion and put in energy to remove a third electron, I get an ion that's 3+, and that ionization energy is bigger than this one, which is bigger than that one. Large jump in ionization energy when removing less shielded core electrons. So that's what we were talking about here, where there's a huge jump here because those were the valence electrons, those are core electrons. Same thing here. This is the valence electron, this is a core electron from a different energy level, or an inner energy level. So let's look at a couple of questions here. It says, consider the following successive ionization energies in kilojoules per mole of elements X and Y. So there's element X, there's Y, and we're looking at the first, second, third, fourth, fifth, and sixth ionization energies. So letter A says, in which group is X likely to be found? So if you take a look at X, look at the first ionization energy, 513, and then it jumps up to more than 7,000, right? That's more than 14 times. And then it jumps again from 7,000 to 11,000. That's less than double, right? So what does that tell us? That tells us that X has just one valence electron, because once we remove it, now there's a huge jump because I'm removing inner electrons, right? So that tells me that it's in group 1 because it has 1 valence electron. Okay, how about letter B? It says, in which group is Y likely to be found? So Y, let's look at it. We have about 700, then we're going to 1400, so about doubles. Going from 1400 to 7,000, almost 8,000 here. Ooh, that looks like it's a almost 6 or 7 times increase. So it looks like the big jump goes from the second to the third. And then look at this one. Going from here to here, that's less than double. Going from here to here, that's less than double. Going from here to here, that's less than double. So it definitely looks like we have 2 valence electrons here. So that must be in group 2 because it has 2 valence electrons. Part C says there are only 3 ionization energies listed for X. Suggest a reason. Well, if there's only 3, that might mean that we only have 3 electrons. This is actually, if you look at the table above, not that you would have that on the test, this was actually lithium. Look at that. So that's because it only has 3 electrons total. All right, so that's it for ionization energy. I want to very briefly talk about electron affinity and electronegativity real quick. Those trends are not going to be on the AP exam, but it is something that you need to know for college. We've talked about electron affinity before last year in detail. Electronegativity will need to know the trend, but not for the purposes of periodic trends, but for the purposes of polarity later on. So let's start with electron affinity. Electron affinity is the energy released or energy transferred when an atom gains an electron. It's kind of the opposite of ionization energy. Affinity means liking. So the higher the electron liking, the stronger the attraction, basically. The more the nucleus likes the electron, the more energy is willing to pay for it. So the more energy is going to be released when it gains that electron. As you go across the period, that increases because you have more protons in the nucleus, so your net coulombic attraction between the nucleus and the valence electrons increases. And so because there's such strong attraction, that nucleus really wants those electrons, it's willing to pay more energy when it gains those electrons. As you go down, it decreases. That's because your electrons are added to higher energy levels, so there's not as much attraction between the nucleus and the valence electrons. And so the nucleus is not going to release as much energy in order to gain that electron. Okay, and electronegativity is the tendency for an atom to attract electrons to itself in a bond. By the way, electron affinity is an energy, so measured in kilojoules per mole. This has no units. It is all relative. Again, you do need to know the trend for electronegativity, but we'll need to use it in more practical ways when we get to polarity and so on. So I want to mention the trend here. So if it's a tendency for an atom to attract electrons to itself, think about this. If you have more coulombic attractions, the atom will attract the electrons more. If you have less coulombic attractions, then the atom will attract the electrons less. So as you go across, it increases. This one decreases. And so it's the same, really, reason. You have more protons or higher nuclear charge. And so your net coulombic attraction between the nucleus and the valence electrons increases, and therefore higher tendency for an atom to attract electrons to itself in a bond. As you go down, same reason as all the other ones, your valence electrons occupy higher energy levels, so they're farther away from the nucleus, so the net Coulombic attraction between the nucleus and the valence electrons is lower or decreases, and so lower tendency for an atom to attract electrons to itself in a bond.